Yeah, hi. Good afternoon. I'm Irfan Shah and welcome to Inside Perception. Uh, Today we are going to read through or discuss the main concepts of planning and a satisfiability paper by Henry Kautz and Bart Selman, which was published in 1992. It's a very influential paper with over 1300 citations, and my research direction is also in planning via QBF solvers, which are very related to satisfiability. Basically, this is the cornerstone of planning via QBF, which is my research area. So today we are going to briefly discuss the basics of planning and the basics of satisfiability very briefly, and then focus on the core idea of this paper, which is taking a planning problem and encoding it into a Boolean formula and using a SAT solver uh, to extract a plan. So, which is the core idea of this paper. And then we will briefly look at the results and make some comments when necessary. And finally, I will show you a demo of a tool that I am building. Basically, I have implemented this encoding, which takes a planning problem and encodes into SAT encoding, and then we can use a SAT solver to solve it. So this is a public repository. You can have a look at it and play around with it. Um, uh, Try to extract plans from planning problems. Okay, before we go into the details of this paper, first let us think about what is planning. So maybe you might have heard about robotics, where there is a robot, there is some environment, and there are some constraints, and the robot needs to take some actions. Does it need to go to right? Does it need to go to left? Does it stop? Etc. etc. So automated planning, which is another name of planning, is essentially generating the sequence of actions that a robot or an object or environment need to do to attain some goal state. So that is the core idea of the planning. And now let us look at a basic example. It's a classical example. Uh, Here, okay. Consider a block solved problem where, if you look at here, there is a table, and on the table there are some blocks with labels, and then there is this an arm like a crane, but it can move on its own. You have to assume it's a very bad drawing, but yes. And then here we have some actions that are possible. First, we have some predicates which describe the state of the problem, like table. A is on table, B is on table. Holding A is not the crane is not holding A. Crane is not holding B. So this one will represent this particular state. Now, if we do an action, let's say the crane picks A, then what happens? The table A is not on table, so we will describe it as a not, and then B is still on the table, and then crane is holding A, but crane is not holding B. So essentially, you start from one state, which are represented by, which is just a set of predicates, which represents one particular state of this problem, and then you have an action like pick A. The crane will pick A, and then it will change into some other state. And there can be many possibilities. It doesn't need to only pick A, it can pick B. And when you have a complicated problem, there can be many possibilities. And this particular let's say graph is like an automata. It's a graph, and the edges are labeled with these actions that are possible, and each node is labeled with the set of all predicates that describe a state. And now let us look at the standard format that these planning problems are represented, which is PDDL specification. If you look at a classical problem that we were looking, block solved problem. So there are two files that describe these problems. One is domain file and another one is problem file. Okay, this is a PDDL specification, which is a standard specification for planning problems. And the main things we need to understand right now, just the basics, is that the predicates describe the state as we discussed earlier, and then there are some actions, and the actions will only happen when the precondition holds, and after the action happens the post condition holds. For example, the one we are discussing, in the precondition here, for us to be able to pick A should be on the the arm should be empty. If the arm was not empty and it was holding B, we could not pick A, right? So that is a precondition. And then once we pick A, the holding, the crane or the arm will hold A. So it has to happen. So that's why the holding A will hold after in the post condition. So this is essentially a formalization of all the things that can happen. So when you pick up an X, then X won't be on the table, and X will be, the arm will be holding the X. Here X is a parameter that can be substituted by objects. And then there are different options. So this is the domain file, and then we also have something called problem file. So in the problem file, we will get information about what are the objects that are present. As so here we only have 2 objects. In this particular file, in this particular problem, we have 4 objects. And then we will get an initial state like this, where B is clear, D is on the table, but B is already on the C, etc, etc. And then our goal is to attain this one. D should be on C, C should be on A should be on B. So this is a classical, in general, a planning problem. It doesn't need to be blocks world problem. It can be something like scheduling. It can be I can show you some more examples. Let's say so these are all the benchmarks, the classical benchmarks. And then there can be these traveling salesman problem, TSP. So the domain will be something like this. We can move, the predicates will be at or visited, etc, etc. So there are many possible ways to represent planning problems. And now the question is, what is satisfiability? So let's go back to our explanation. And so if you look at here, this is a Boolean formula where X, Y and Z are Boolean variables, where Boolean variable essentially means it can be either 1 or 0. And then they are connected with ands, ors, ands and nots. So a Boolean formula is simply a, let's say, how do we say in layman terms, like they are connected with these connectives, or and not, then it's called a Boolean formula. And now, what does this satisfiability do? So why is it so important? In satisfiability, so we call it SAT problem, where you give some formula like this, and then you have to get an assignment where if you say X is equal to 1, Y is equal to 1 and Z is equal to 0, then does the formula evaluate to 0 or 1? And the question here is, can you find an assignment for these variables such that this will evaluate to 1 or true? Now this is an NP complete problem. That means all the problems inside the NP class, it's a class of problems, can be reduced to Boolean formulas, SAT problem, and then we can use a SAT solver to solve this SAT problem. So that is a core idea. That means you don't need a different algorithm for different problems. You only have one general input format, and then you can write any problem in this particular input format and use the SAT solvers, which are beasts of computation, which are really, really good. So what this paper does now, if you go back to our paper, so the authors, what they proposed is that we can model the planning problem into satisfiability problem. So that is the core idea here. As now we have discussed the basics of planning and satisfiability, let's move on to the fourth session. Yes. So as we looked at our example, this is also something similar. It simply says that at timestamp 1, A is on B and B is on table, A is clear, P is on A at the timestamp 3. That means we have looked at it like this, right? So we are at here. So one hop is like one timestamp. And so what essentially what we do here in the encoding is that we start from some state, like an initial state, something similar to this one, and then we make these hops using the actions, and that is modeled by a transition function. A transition function is simply all the actions that are possible. And then the idea is that you start from initial state, then you make some k hops, and then you should reach this goal state. Now the $1 million question is that what are the actions we need to take such that you can go from I to G, initial state to goal state? Is there one? If it is there, can we find it? And now how do we do it in terms of SAT encoding is that for every action, as we looked at here in the domain file, let's suppose we have pickup action. We simply say if pickup with a parameter is true, then we say all the preconditions should hold in ith step and all the post conditions should hold in I+1 step. This is the core idea. If we go back to our section 4, if some move, which is an action, is true, that essentially means the preconditions must hold and post conditions must hold as well. That is the key idea here. All right. So what we will do now is that we will look at the concrete encoding at a later point. But first we will look at the results the authors got in these and some observations they made. One of the observations the authors made is that when you have an action with a lot of parameters, more than 2, then they will result in large clauses and large variables, like which can be avoided. And what they propose is that when we have a big when we have an action with a lot of parameters, we can break it down into a lot of actions with only 2 parameters. So this is just one of the experiment. They showed that the number of clauses and the size will be decreased, even the number of propositions. And then they also try to compare with 2 different approaches in SAT solving. One is randomized SAT solving, and another one is like DPLL, the classic SAT solving. They found that the DPLL SAT solving is quite good, and they didn't find any significant difference with the randomized SAT solving. Okay, now we have looked at the basic idea of the encoding. We will now go to the implementation that I have implemented, and we'll look at the encoding and we'll try to play around with the tool, and then we'll wrap it up. Okay, first let us go to this tool. This is a public repository. You can have a look at it and you can play around with it. If we go to the SAT encoding generator, basically what it essentially does is it generates the initial gate, as we looked at here. So it generates the initial gate from the problem file from here at time step 0, and then it generates the goal state at the timestamp k+1, assuming that we need k steps, and finally it generates these transitions between each of these pairs, k of them. So generating k transitions. So that is what it does, and then it outputs the encoding in circuit format. Okay, let's try to run it. And okay, first we will, so this is in Python, and so first we need the domain file where we have test cases, blocks world domain file, which is what we looked at right now. And then test cases, we also need the problem file. We take 4 objects file, the one we used for the example, and then we say what is the length of the plan we want, the k. Let's try with 5 first. We try with 5, and then we give which file the encoding should be returned to. Let's call it encoding. And then we are running a planner. We are running a SAT solver. This is essentially a QBF solver. And we want to have an output of it. QBF output file. And then we need to give the QBF solver or SAT solver path, which is Kautz here. Kautz is a QBF solver. Okay, we need one more. What are we missing? Let me look at the main file. Okay, so we need a k, then encoding. Oh yeah, we need to say that it is a SAT solving encoding. So because I already have a SAT encoding and a QBF encoding, I have to differentiate it. Okay, now let's try to run it. So now what happened is it tried to find a path of length 5 as we looked here. So it tried to find 5 hops, but it seems it didn't find any such plan that can be possible, that we can go from the from this initial state to this goal state. So now what we do is we try to increase the length of the plan. So 10. So now we got a plan with some actions that needs to be done. Let's say, okay, the unstack. So you need to unstack B from C and then put down the B, unstack C, A, blah, blah, blah. And then these are the sequence of actions, which is essentially plan that the crane needs to do in a sense. Okay, and then we also have a tester whether which tests whether this plan is accurate or not, and the plan is also accurate here. Okay, so this is a demo of our tool. You can have a look at it, what is going on in the tool here in planning. I will add the link to the repository as well. You can fork it and you can play around with it. I will continue to do the development, and because I will also do this QBF encodings later, which we will look at in the upcoming videos. Alright, so and furthermore I have few more comments here. So satisfiability, planning where satisfiability is quite significant. It had a lot of success, but the main challenges is that oh yeah, we forgot to look at the encoding, right? The concrete encoding that is generated. Yes, it should be somewhere here. Oh, this is yeah. So this is the encoding that is generated for our problem, and then these are all the variables, blah blah blah. So this is the initial gate. So initial gate in the sense, because I'm doing a circuit based encoding, so this one represents the initial state, this one, and then the goal gate, it will be somewhere down here. This one will represent the goal gate, and well, you can see that this is quite large encoding, and if you look at the size of it, it's already 245 KB, And if we try something large, if we try to do something large, let's say with 8, plan not found, but let's look at the size of the plan encoding. So it's already 2.3 MB, and if we increase the length of the plan, it will increase proportionally. So let's say 30, and then you can see that the encoding is now 7 MB. And in general, the plans are quite long, and the transition functions that we are generating for the hops are quite large. So the SAT encoding, the main drawback with the SAT encoding is that the encodings become very, very huge. Yeah, so 7.9 MB, it can goes to GB and even terabytes. So that is the reason why we are moving from satisfiability to QBF encodings, which we will discuss later in our videos. But that is the main bottleneck. So there are many problems where you can't even run the planner to even extract a plan. Yeah, I hope this made a bit clear. And have you ever used such solvers to solve any problems, or do you have any doubts with these planning via satisfiability? And if you have any comments regarding, do we need to go even deeper into these papers, or is the overview enough, let me know in the comments. And that's all for today. Thank you and see you soon.